Hey everyone, my name is Teodor Bozhanov. I'm a third-year student at the University of Manchester, currently studying aerospace engineering. And this is my project with a colleague of mine, which couldn't make it today. So first of all, I'd like to express my gratitude. This is my actually first time presenting at a workshop and a conference, so thanks to everyone. So let's get down to business. What to expect here? So we're going to start with a brief overview of what I'm actually doing, some of the motivation behind it. Then we're going to move to the existing research and technology in this area. Some of the preliminary numerical analysis that I've done towards simulation, the results that I actually obtained from the simulations, and then we're going to finish with some extended technology and some future work. So moving on, this study actually focuses on small satellites at very low Earth orbit, between 100 and 300 kilometers of altitude, and tries to identify potential electropropulsion system and atmospheric breathing electropropulsion systems which can be used to compensate for the drag experience at these different types of altitudes. In addition, we are trying to find the trade-off zone between electropropulsion and atmospheric breathing electropropulsion, i.e. at what altitude is better to use ABP instead of EPs. Now this research is more conceptual design, and it actually tries to lay out the framework for any potential future analysis. So let's continue with the motivation. So why are we going into that low orbit? So why do we need to go at 100 or 200 kilometers of altitudes? Well, first of all, the ground resolution improves significantly. As you move further down, the instrumentation that you need for like lenses and stuff reduces, the size of it reduces. So if you were to keep the same size, you're going to have an improved resolution. Or if you want to keep the same resolution as before, you can decrease that size. In addition, the breathe density is significantly reduced simply because the lifetime is so short. So we don't really need to worry about end-of-life orbiting capabilities or such sort, and we're going to be able to meet OESA's requirements on the orbit. But why small satellites? Well, frankly, because we can, and they're quite useful. Back in 2001, a study conducted by a Serbian university stated that 95% of the performance of large satellites can be achieved by small satellites for 15% of the cost. Now, this research was done almost 16 years ago, so undoubtedly the steps have improved and are going to keep improving. And in addition, projections from the House of Commons actually show that between 2015 and 2019, more than 500 satellites, small satellites, are going to be launched, which is going to be equal to around 7 billion of market share. And as you can see here, a space work forecast says that for Earth observation and remote sensing, the ratio of satellites is going to be around 73%, which is quite big. So we need more research in this area. So why electropropulsion? Well, electropropulsion, as you've seen before, is quite efficient. It has high delta-V capabilities. The thrust ranges are small, but we don't really need big thrust ranges for these types of mission. The electropropulsion system can be made very, very tiny, and there's a wide variety of options available that we can choose from. So moving on to existing research and technology. Now there's a lot of satellites incorporating some sort of electropropulsion systems, and some of the satellites actually use the electropropulsion system as its prime source of propulsion. One of these is actually Smart 1. It's a fairly big satellite, around 300 kilograms, and it was actually one of the first satellites to leave Earth's sphere of influence and to orbit the Moon. And it did that only with 82 kilograms of xenon gas. Now, one of the engineers reported that the mission was extended due to the automatic capabilities of the subsystem, which is quite nice. Something more close to the research that I'm looking at is Gochi. Now, this satellite operated between 250 and 270 kilometers, and the prime reason for its propulsion system was actually drag compensation. So we can see that drag compensation is actually possible. However, this satellite was fairly big. It was around 5 meters in length and weighed about a ton. So we can look at something smaller. In terms of actual research and papers produced, there isn't actually that many papers conducted on drag compensation. Most of the papers focus on altitudes above 300 kilometers and above 400 kilometers, and at fairly large satellites. moving on to EP and AVP system, there's actually plenty of research conducted on EP and micro EP systems. However, AVP systems are still in the gray area, if I might say. Although they've been existing for almost 50 years, there's still not too much research done in this area. And there isn't actually a comparison between EP and AVP systems and how they can be traded off. So numerical analysis, this was a preliminary analysis that actually made it possible for the simulations to run. So we needed to evaluate all the different things that are happening actually in the low Earth orbit, so that we can be able to model the evolution of the orbit quite well. So starting with atmosphere models, initially we evaluated about 5 atmosphere models, and we chose the NRL and SCD. That's a long name. And we stuck with it. The drag forces were about 0.5 newtons at around 100 kilometers, ranged to about 20 micronewtons at around 300 kilometers. Now, we found some small variations due to relative position of the satellite with Earth and effects such as space weather effects and position and time of day. Actually, you can see here that the solar flux variation of 500 kilometers accounts for around 900% change in drag force, whereas if we move down to 200 kilometers, that change reduces around 75%. So we took all that data and we actually made a propagator. The propagator accounts for 5 perturbing forces. It is able to monitor the changes of orbital parameters with a relative degree of accuracy. In addition, this propagator allows us to put thruster models quite easy, and some of these thruster profiles are actually here. We chose 3 different types of electric propulsion systems. One of them is an ablative closed plasma thruster, which is a very simple system, but the efficiency is not that great. The other one is a medium-range ion thruster. It's a radio frequency ion thruster with a relative middle efficiency, and then we went to the highest efficiency with field emission electric propulsion system by Protec. Moving on to the other part, which I mentioned earlier, the atmosphere breathing electric propulsion system. As you can see, it operates exactly as you think it is. It has an inlet which literally scoops the atmospheric gases, which are then either stored in a propellant tank or they're directly accelerated using some sort of electric propulsion system. And the 2 main components here are actually the inlet and the thruster. So we're going to look at each one of them individually. So for inlet, you can have 2 types of inlet. One of them is just a long angular intake, which is an intake in front of the satellite, and the other type is a bypass, another intake, where the satellite core is in the middle. So the long annular intake is a simpler design. It has a long duct, which allows for forming a compression zone behind at the end of the duct. There's some duct stores in the beginning, which prevent a potential backflow of the flow. And the DSMC analysis, the direct simulation multi-cloud analysis of the collection efficiency, which is the ratio of the flow going into the system and the flow actually used by the thruster, so ranges between 17 and 23%. On the other side, we have a bypass annular intake, which is a similar thing, except the satellite core is in the middle. Again, we have a long duct which allows the forming of a compression zone at the end, but this time the particles are actually scattered from the satellite core and fed into the thruster. And the DSMC analysis of this type of system shows a collection efficiency of around 40 to 50%. Now, collection efficiency also can be increased by implementing a turbomolecular pump. However, that introduces a bit more challenges and it makes the system more complicated, but collection efficiency are seen to range to about 60%. Some of the considerations that have to be taken into account in this one is the intake area ratio and the relationship between the intake area ratio and the mass flow rate. As you decrease the intake area ratio, the collection efficiency actually increases. However, the mass flow rate decreases and therefore your thrust decreases. So there's some trade-off between these systems which have to be considered for small satellites. In addition, compression of the atmospheric gases, particle differs, the type of intake are also going to be some things that have to be taken into account when designing this system for small satellites. The thruster that we're using is a inductive plasma thruster. This thruster has a lot of benefits associated with it, since most of the gases that we're going to be using are corrosive in nature and oxidizing in nature. We're using this in different plasma thrusters because it doesn't really matter with what kind of gases we're going to be using. In addition, the plasma that comes out of it is already neutral, so there's no need for neutralization, significantly increasing the lifetime of the system. Now, the only problem with this one is that the power required is quite big. It varies from 2 to 10 kilowatts. But researchers at the moment are actually working on that and trying to bring it down as much as possible. Moving on to the main findings. Before we start, we're actually presenting the main findings and the lifetime increase that we see with the implementation of these systems. We have to have a control orbital here. So these are some of the results that we got from the propagator. The satellites are 1, 2, and 3 unit satellites, positioned on 4 different types of orbits. So at 300 kilometers, the lifetime is about 56 days for one CubeSat, and it varies down to 4 hours at 150 kilometers, which is significantly reduced. So if we plug everything in with 30 grams of propellants, the PCC system and the RIT microX system can achieve full drag compensation and actually increase the lifetime by around 196 to 288 days, which is significant enough and can be considered for future mission. Unfortunately, the FM Nano is a bigger system and cannot be implemented into a 1-unit CubeSat. Moving into a 2 units, we see a similar trend. The thrust actually increases 2 to 4 times. However, here we can implement the FM Nano, which you can see it gives, with a 2-unit CubeSat, around 124 days of lifetime increase. And this obviously drops as we move down to lower altitudes. Similar thing is seen when using 3 units. However, the thrust ranges increase significantly, and we're actually going to be needing a lot more propellant to run it. So there's going to be a lot more trade-off between the actual subsystem of the satellite and the proportionate subsystem of the satellite. All of this is summarized here. You can see that the reduction of orbital decay is actually greater at lower altitudes. So we have around 700% increase of lifetime at around 200 kilometers with the ion system on board. While done some testing with 150 grams of propellant, that's unit CubeSat, equipped with the FM Nano, we'll be able to raise its orbit by 1,200 kilometers or change the potential by about 4 degrees. This is more or less equivalent to 1 kilometers per second of delta V. The other thing that has to be considered is that the thrust lifetime significantly reduces as you go down in size. The other part is the atmosphere reading light propulsion system. The thrust atmosphere reading light propulsion system is actually a function of both atmosphere and intake geometry. So for this particular case, we've chosen an area ratio of around 10 and a slightly higher collection efficiency of around 0.58. However, this gives us a thrust drag ratio of 2.87, purely on theoretical and analytical calculation. We can see that the full drag compensation is actually achievable. If we actually move to the simulation and inputting this thrust model into the propagator, we can see that a full full compensation of drag can be achieved from about 120 to about 250 kilometers. 250 kilometers is a bit sketchy zone though. And an increase of 42,000% at 180 kilometers is seen for 200 hours of lifetime. Now the lifetime of the thruster will be significantly limited. It's gonna vary depending on atmosphere composition and altitude. So I've chosen a fairly conservative value. So a trade-off zone between EP and AVP preliminary is seen around 250 to 200 kilometer range. As we move down, the thrust actually increases significantly, and the current EP systems cannot provide the thrust required. So about technology and extension, we've seen talks about missions to Mars and some presentations before. This can actually be employed in Mars. At around 100 to 130 kilometers, the density is actually similar to that of Earth at 300 kilometers. So you can have much greater resolution of the planet, and it's going to be quite suitable for exploration missions and potential future colonization missions, because you will be able to provide some communication and observation. Similarly for the Jovian and the Sidonian system, although it's going to be slightly more challenging putting CubeSats there and essentially small satellites incorporating atmospheric breathing and propulsion system. It is possible, and the gases of the Saturn and Jupiter are actually the atmospheric composition of them is actually quite favorable for atmospheric breathing. So we can have a swarm or even a fleet, as someone mentioned before, around the planets, which are going to be dispatched to different moons. So, concluding remarks, we saw a substantial increase of orbital lifetime by implementing electric propulsion systems. It varies from 6 to 700% depending on the type of electric propulsion system. We've seen that the lifetime is actually higher at, the increase of lifetime is actually higher at very, very low orbits. Increased operation capabilities by allowing orbit raising, so we saw that we can change inclination and such. We can also implement ADP system into small satellites. However, theoretically it's possible. Practically right now it's still not possible. However, we are working on it. So we found a trade-off zone between EP and ADP around 200 to 250 kilometers per second, and we saw that interplanetary propagation is actually possible. So what some of the future works that we're going to be doing? Unfortunately, the propagator could not account for variation of thrust. As you know, the thruster probably wouldn't be operating at full time. There's going to be periods of eclipse and such. So one thing would be actually to be able to implement the variable thruster modeling. In addition, once we've gone down to the thruster modeling of the ADP system, it would be nice to incorporate the gas surface interactions between the outer and the actual intake and the inner parts of the system. What I'm very excited about and what the University of Manchester is undertaking is we're going to be developing a hyperthermal atomic oxygen wind cell, which is supposed to simulate the environment seen by satellites in very low Earth orbit. And that's going to enable us to model these interactions much better and potentially identify materials and weight for which to reduce that drag and increase the satellite lifetime. So more information about all of these can be seen in the reference slide. Thank you all. Any questions?
All right, we'll take questions.
Thank you. Very interesting talk. At 200 kilometers or so, you're in already a highly variable plasma, and your last slides spoke to that. But it really does vary a lot, day, night, season to season. Have you factored that into the performance?
Yeah, so the performance of the thruster or the performance of the satellite in total?
The performance of the whole AV.
Yeah, so when I was doing the evaluation of actually the atmosphere models, there's a huge variation in density due to solar wind effects and such and such. Some of these thrusters can actually compensate for these variations. The orbital propagator, the atmosphere model implementing the orbital propagator tries to also to compensate for these variations as much as possible, and that's why at some of the plots actually you see that massive variation in eccentricity and such. But potentially that could be a big problem because if you get a quite high variation in eccentricity, that could bring you to lower altitude at which the thruster would not be able to cope, and inevitably it's going to bring stuff like down.
I wasn't just thinking of the density variations, I was thinking of the ionization variation.
The ionization variation has not been accounted for in the thruster model, no, not yet.
Sounds like a big problem.
Yeah. Hopefully in the future.
You mentioned in the air-breathing electric propulsion that a compressor is needed.
Not at all times, but efficiency is improved with compressor.
So does that compressor need to also consume electrical power?
Unfortunately, yes.
And have you factored that into
not in this session. So this version of the type does not incorporate a compressor. The compressor increases the collection efficiency but not by a great margin. So you can have an acceptable collection efficiency with a smaller intake. However, there were some papers that I looked at that had an incorporated compressor, which it was a system that was tested independently. So we just had an intake, the SMC evaluation of the intake, and then experimental evaluation of the compressor. And the compressor actually did not require that much power. However, if you put a compressor inside, with the system in place, the overall power requirement I think is going to spike quite a bit. And you have more potential failure as well due to the complexity of the system. Because the flow it's highly molecular, so the compressor has to be able to cope with that. In addition, the atomic oxygen could, I don't know the interaction of the atomic oxygen and how the interaction of the atomic oxygen could potentially change the working of the compressor. This is going to be quite interesting to see, and this is what we're working on at the moment as well.
Just a couple of suggestions.
Yeah.
One was thruster technologies for the air breathing. We might look at other technologies like gridless ones like air.
Yes, we looked at HETs, and we looked at also ion propulsion. However, I chose that one because the thing that we're working on right now is developing this kind of technology, and potentially in the future we're going to be combining both technologies. So I wanted to look into that second one. But yes, you're right, and there actually have been tests with HETs working on with O2 and N2, and they seem to work quite well, although the lifetime is slightly reduced.
Exactly. The other one was maybe, I don't know if you considered slightly larger spacecraft.
Yes.
Presumably you'd like to fit a payload in.
Exactly. For the type of atmosphere breathing, I consider a 3U, which is very, very conservative, and it's probably not possible. I just wanted to evaluate how small intakes are going to be affecting the performance. But much bigger satellites are probably going to be for dimension of 12U satellites, and by seeing the dimensions and everything, I think much bigger satellites, considering that atmosphere breathing and propulsion, would be much suitable.
Great, so let's thank our speaker again.